We're deriving the formula for arc length when we have a curve C that is being traced out by some vector function. As a reminder, the arc length can be calculated by looking at the antiderivative of the square root of f prime quantity squared plus g prime quantity squared, and then we integrate that from the values of the parameter that start and finish the section of the curve whose arc length we're measuring. And a more compact and convenient notation for this arc length formula is that the integrand is the magnitude of the derivative of the original position vector function, or the magnitude of the velocity vector. So we begin again with that declaration that C is traced out by some vector function where the x component is a function of the parameter and the y component is a function of the parameter. If we were to differentiate both of these parametric equations, what we get is the derivative of x with respect to the parameter, which can also be expressed using prime notation, and the derivative of the y component with respect to the parameter can also be expressed as g prime at t. And one other declaration is that we want C to be traced out from left to right, and the derivative of an increasing function is going to be a positive value. So we'll make note of this and use it again in a moment. So let's take a look at a little concept drawing here where we have a curve that is the path being traced out by the vector function. And let's consider two specific vector outputs that start and stop a region of that path whose length we're going to focus on. Let's call this first vector output r evaluated at alpha, which is going to yield an output vector where my x component is f at alpha and my y component is g at alpha. And the second vector terminates at the point that finishes the arc length, and this vector is determined by plugging beta into these parametric equations as well. So our derivation is giving us a formula for calculating this arc length here from the tip of r at alpha to the tip of r at beta. Now let's recall that we could trace out this curve with a scalar function, y is equal to f at x. Scalar functions don't give us as much information as vector functions when we're considering tracing out a path. For example, if we looked at the derivative of the scalar function, which is dy dx, or how the y changes with respect to how x changes, this gives us f prime at x, which gives us the slope of the tangent line. So if we were looking at a tangent line here, the derivative of a scalar function only gives me the slope of this line. But if I were to look at the derivative of the vector function, what the vector function gives me is a derivative vector that not only points in the direction of the tangent line, but it also has a magnitude which represents the speed of the particle at that moment. So we get more information out of the first derivative if we calculate the derivative of a vector function as opposed to just a scalar function. But sticking with the idea of the scalar function for now, these points that would start and stop the section of the arc whose measurement we're after would be given by x values, the x value A, and let's say the x value B, that start and stop that arc length. And let's also recall from Calc 2 that the measure of that arc length would be calculated by an integral from a to b, where the radicand is 1 plus f prime at x, quantity squared, and we integrate with respect to x. So we're going to begin here. We're going to begin with this older formula for arc length and build on that to try to develop the arc length formula for the path being traced out by a vector function. So as we said a moment ago, if we were to differentiate this scalar function, we get dy dx, and that can be interpreted as f prime at x. So we're going to substitute dy dx into this arc length formula. So we have arc length is equal to the integrand from a to b of 1 plus, now we'll say dy dx here instead of f prime at x, quantity squared, and then the integral is evaluated with respect to x. Now what we want to do is we want to introduce the parameter t and eventually get the integrand to depend on t and evaluate with respect to t. So in order to do that, we're going to pull an algebra move right here and rewrite this integrand where that fraction is a complex fraction. We'll write the numerator as dy dt and the denominator as dx dt, and then we're going to quantity square that and integrate with respect to x. This complex fraction here would simplify down to being the dy dx that we came from, and we write it or expand it to include a small change in t. And then additionally, we're going to multiply here by a well-chosen 1, small change in t over small change in t, and we'll use this ratio to help us complete the migration over to the parameter t. Now let's recall from the beginning of this video that x was equal to the parametric equation f at t, y was equal to the parametric equation g at t, and dx dt was the first derivative of my parametric equation for x, and dy dt is the first derivative of the parametric equation for y. So we'll just sub in f prime at t and g prime at t for these dx dt, dy dt's in the integrand here. Now we're in the middle of the migration from integrating with respect to x to integrating with respect to t. So while we're kind of in transition, I'm going to leave off the limits of integration and focus just on the integral. So we have the square root of 1 plus, now we can simplify this complex fraction to being just g prime t in the top and f prime t at the bottom, and the prime notation makes it quite compact. We still have dx out here, and we are still multiplying by dt dt, but let's split this up into 1 over dt times dt over 1 so that we can then move these two fractions together, multiply these together to become dx dt. Now let's see where we are. Under the radical here, let's get a common denominator of f prime t quantity squared, so that'll be plus g prime t quantity squared in the numerator, and all of this is over f prime t squared in the denominator. And we now have dx dt out here. We're multiplying by a small change in x divided by a small change in t, and then we still have our dt value out here, which is now declaring our variable of integration to be t. Again, we're going to substitute f prime at t in for dx dt, and we should be all in terms of t now. So we'll bring our t limits of integration. The value of the parameter that started the length of arc that we're measuring was alpha, and then beta was the one that terminated that arc length. I'm going to split this integrand into a numerator that is f prime t quantity squared plus g prime t quantity squared, and in the denominator we have the square root of f prime t quantity squared. Now again, we still have the f prime t value out here, and we also have dt as the variable of integration now. So let's recall from the beginning where we made several declarations that x was increasing, which means that dx dt, also considered to be f prime at t, the first derivative of the parametric equation for x, was a positive quantity. If f prime is already positive, then the square root of f prime squared is going to be just f prime, and we don't have to wrap it up with abs-val bars because f prime is already a positive quantity. And this f prime in the denominator of the fraction is going to cancel with the f prime that we have up here. So let's try to bring all of this together. We now have the antiderivative measured from alpha to beta. We only have this numerator here, which is the square root of f prime t quantity squared plus g prime t quantity squared, and our variable of integration is just dt. So this is the formula for arc length that is going to measure a portion of a curve that is defined by a vector function. A more compact notation for that, though, again as a reminder, is just to say the magnitude of the first derivative of the position vector, which can also be considered the magnitude of the velocity vector. And these are the formulas that we were trying to derive.